Hello, my name is Yannick Trache, and I'm a professional engineer with an MIT degree in aerospace engineering. I spent most of my career in nuclear engineering, but before that, I helped start Spectral Applied Research, which helped build Canada's first space telescope, the MOST telescope. I helped operate a LiDAR observatory that monitored the ozone layer over the Arctic. And more recently, I've become very interested in the problem of climate change, and I'm very active in advocacy about it. I'm the chair of the Toronto chapter of Citizens Climate Lobby. I was trained by Al Gore as part of the Climate Reality Project. I went back and took extra classes on climate science from MIT and from the University of Melbourne, and I am the president of Engineers for Carbon Ethics. Today I'm going to talk about carbon capture and storage. This is a repeat of a talk that I gave for Citizens Climate Lobby at their national conference in Ottawa on November 22nd, 2014. We tried to record that talk, but unfortunately that recording didn't work, and so I'm re-recording it now so people can refer back to it. So I'm going to start by establishing some common ground on renewable energy with my audience, with my main audience being climate change advocates. And then I'm going to whet your appetite by showing that some very smart people are telling us that we should take a serious look at carbon capture and storage. But before I can explain exactly why, we've got to get an understanding of exactly what it is and what the different options are. And once we have that background, I hope that I'll be able to make a convincing case as to why we need it. And then I started a discussion about how this would play into Citizens Climate Lobby's fee and dividend policy, which is the main thing that they work towards. What you see here on this slide, that's me from a year ago. When another engineer first told me that I needed to take a closer look at carbon capture and storage, this is basically how I responded to him. Because let's be clear about something. Let's get something straight. It is technically feasible to supply the world's energy demands from renewable sources alone: wind, solar, hydroelectric, and biofuels. And this is not a matter of opinion. This is science. This is a conclusion of the Intergovernmental Panel on Climate Change, the largest formal literature review ever undertaken by mankind. Now, there are some limits that you hear talked about a lot that say that we can only have 20 or 30% of our electric grid be renewable, and the rest has to be something else because of the intermittency of wind and solar. And that assumes that our transmission grid stays static, essentially. That if we build a supergrid that can share electricity across time zones and across areas that are larger than an atmospheric circulation cell, and here we are talking about thousands of kilometers across, then it is in theory possible to use renewables alone to provide our energy. Possibly storage technologies will help us as well. And of course, the big part of that strategy is to back up the intermittency of renewables with hydroelectric power and geothermal, as opposed to backing up renewables with natural gas, which is the way that it's done in many places like Ontario. Okay, so we've established that the renewable strategy can work. So why do we need carbon capture and storage? Well, one reason is economics. At Citizens Climate Lobby, we like to say that we can address climate change without hurting the economy. But if you dig through the reports that we use to support that, if you look at the REMI report, you can see that this forecast relies on significant growth of nuclear power and carbon capture and storage. The Stern Review, which is widely known for predicting that we can solve climate change while continuing to grow the economy, made similar assumptions, especially when it comes to carbon capture and storage. Extensive carbon capture and storage will be necessary to allow the continued use of fossil fuels without damage to the atmosphere. But the most important reason to use CCS has to do with this number. The world's politicians have agreed to try to stay within 2 degrees Celsius of pre-industrial temperatures. This is an ambitious goal. In fact, at the monthly telecon of Citizens Climate Lobby at the beginning of November, our guest who was on wrote that this target is effectively unachievable unless we make heroic assumptions. Now, at the Ottawa conference with the CCL members present, I asked them what they thought about that. I asked if there were any heroes in the audience, and the answer was a resounding yes. There are lots of people who want to strive for this 2 degrees Celsius target, and in fact, there was someone who proposed 1.5 degrees Celsius in the audience. Okay, so if that's our target, what do we need to do to make sure we stay under 2 degrees Celsius? And unfortunately, the science is not completely precise on this point. But roughly speaking, the IPCC's Working Group 1 roughly translate this to getting carbon dioxide concentrations below 450 ppm carbon dioxide equivalent by the end of the century to make sure that exceeding 2 degrees Celsius would be unlikely. So where are we at now? When I asked my audience in Ottawa, a lot of people gave out figures around 400 ppm. That figure is pretty well known. But that's actually only the carbon dioxide levels in our atmosphere is at 400 ppm. This figure, 455 ppm, is in carbon dioxide equivalents. So what that means is that it's looking at all of the other greenhouse gases in our atmosphere. There are other gases that are much more powerful than carbon dioxide. There's less of them, but there's things like methane, that's the most important one, and there are a number of refrigerants as well. And if you count up all of those greenhouse gases and convert them all to carbon dioxide equivalent and add them up, where do you think that we are now, today in 2014? We're at 478 ppm. Okay, I want to give that a second to sink in. We have already overshot our 2 degrees Celsius goal, and we urgently need to remove greenhouse gases from the atmosphere. Now, there's a bit of good news about that 478 number, I should mention, since part of it does come from methane. A lot of the excess between 400 and 478 comes from methane. That means that it would go down on its own if we could stop putting out methane into the atmosphere, because methane has a relatively short life cycle in the atmosphere. And so if we could stop putting it out, the 478 would start to decline on its own. Carbon dioxide, that's the 400 ppm, stays in the atmosphere for much longer. It doesn't come back out of the atmosphere nearly as fast. There's another target that I should mention here, which is 350 ppm. That was proposed by James Hansen, and it's a bit of an older target. It's based on slightly older science than this 455 ppm that I'm showing you here, but it's essentially the same thing. Except that 350 is for carbon dioxide only. So we're talking about reducing carbon dioxide levels from 400 to 350 by the end of the century, and reducing carbon dioxide equivalents, the grand total, from 478 to 455 by the end of the century. Okay? So how do we do that? Well, we have a variety of technological options, and I think that we should use them all. We have a very big problem with climate change, and I think we should throw everything we've got at it. But which technologies are most important? The Intergovernmental Panel on Climate Change looks at this through diagnostic studies, where they assume that one technology is unavailable, and then they figure out how much more expensive would it be to reach 455 ppm with that handicap. And that's what you see on this graph here. The baseline represents using all of the available technologies. So that's nuclear and renewables and biofuels and carbon capture and storage in the most economically efficient manner. And that's essentially the assumption made by the Remy report and the assumption made by the Stern review. Now in the first column here, this is looking at trying to do a nuclear phase out, trying to phase out nuclear power at the same time as we're trying to address climate change. And what this shows is that that would make the problem a bit more expensive, but it's not a deal breaker. I don't recommend that we do this, but if you really hate nuclear, it is theoretically possible to get rid of nuclear and solve climate change if you're willing to pay a bit more money. Okay, now in the second column here, that's called no supergrid, nuclear is back on the table, but what they've removed is large-scale renewable technology. So there's still some renewable energy present in this option, but in this scenario, in these scenarios, we would never get around to building that high voltage direct current supergrid that we would need to be able to get past that 20-30% maximum penetration that I was talking about earlier. So there's a limit on how much renewables we can use in these scenarios. But still, in terms of expense, it looks like we can do it. It's a bit more expensive, but we don't have to have the supergrid. In this third column here, this is looking at getting rid of biofuels. So large-scale renewables is back on the table. Nuclear is present, and we're still using some biofuel energy, but not only the existing technology in biofuels. So the stuff made from corn, essentially, that competes with crops and with forest. In these scenarios, we never succeed in developing the second generation biofuels that would really be made from agricultural waste or algae or other things that don't compete for food. In this scenario, you can see that this starts to be a problem. We're now talking about scenarios that are around twice as expensive to fix climate change as if without those second-gen biofuels, as if you had them. So biofuels is an important technology. Now the fourth column here, that's labeled nuclear plus CCS only, we're going to skip that. That's a bit confusing. I've simplified this chart quite a bit too from the IPCC. I should have cut out this column as well. But let's move on to this column that says no CCS. So this is looking at scenarios where we've got nuclear, we've got renewables with a supergrid, we've got second-gen biofuels, but the technology that's missing here is carbon capture and storage. So this is a scenario where we decide that fossil fuels are evil, we never want to go back there again, and we punish them by completely shutting down that CCS option. And the results are disastrous. Now we're talking about expenses on the order of 2 to 3 times as expensive as the baseline, and that's 2 or 3 times a really big number to begin with. So now we're talking about having a real risk of throwing the world into an economic depression that could last for decades if we don't have carbon capture and storage. And actually, the problem is even worse than this, because you'll note that there are only 4 dots on that column. They actually did 10 scientific studies that looked at this. But out of those 10, 6 of those studies came back and said, you just can't do it at any price. You're not going to be able to get to 455 ppm. And then 4 scientific teams out of 10, 4 out of 10 said, yeah, you can do it as long as you're willing to throw the world into an economic depression. So CCS looks like a crucial technology. Finally, in this last column here, what this is looking at is what if we don't use any technological methods at all. So the idea here would be to just shut down all fossil fuel systems and start planting lots of trees. And what you find here is that there's one scientific study that says that, yeah, maybe we can do it, but the costs are completely off the chart. This option is just crazy to try to fix this without technology. So the IPCC is basically telling us that we really need carbon capture and storage in order to meet 2 degrees Celsius. And by the time I finish this presentation, I hope you'll understand why it's so important. This is the clearest statement that the IPCC says about this, I think, in the text. Many models cannot reach 2100 concentration levels between 430 and 480 ppm if the full suite of low-carbon technologies is not available. The lack of availability of CCS is most frequently associated with the most significant cost increases. No one really said this to me. This is kind of my inner critic talking. Let's look at carbon capture and storage. What is it? It looks about this simple on the surface. A pipe going into the ground. Not very exciting. But here's the exciting part. We're already doing it, and Canada is a world leader. We've been pumping 3 megatons of carbon dioxide per year into the Weyburn and Midale fields in Saskatchewan since 2000. That makes this the largest energy CCS project in the world. But there are about 5 or 10 other projects that are about the same size and over 200 smaller experimental projects around the world. The carbon dioxide that's being pumped into the Weyburn field comes from the Great Plains Synfuel plant, which is almost single-handedly responsible for giving CCS a bad name. Because, you see, this plant takes lignite, which is the dirtiest of coals, and turns it into methane, which is then sent to the East Coast and burned in people's furnaces. So there it turns into carbon dioxide. So if you add that together with the fugitive methane emissions from the lignite coal mine, then the total emissions from this process are about the same as a normal coal plant, even with carbon capture and storage. But before they added carbon capture and storage, this plant was even more polluting than that. So CCS did help. They're building another one of these coal gasification plants in Mississippi, and they're going to be using CCS on this one as well. This is going to be the largest and most complicated coal gasification plant ever built. This thing will be just as expensive as a nuclear plant and just as dangerous as well. This is what Al Gore was warning you about when he said that there's no such thing as clean coal. But you don't need coal gasification plant in order to use CCS. You can install carbon capture and storage on a conventional coal plant. It's a little more difficult to capture the carbon dioxide, but we do have a few different processes that can do that. This project, shown on this slide, also in Canada, went online just a couple of months ago, and it is the largest carbon capture project in the world to be installed on a coal power plant. It will capture 1 megaton carbon dioxide per year from a 110 megawatt plant. That's about as much capacity as one large wind farm, but it can run whenever you need it, not just when there's wind. Another project, the Alberta Carbon Trunk Line, will capture 15 megatons per year, far larger than any other carbon capture storage project of any type anywhere in the world at any stage of planning. This thing is huge. In terms of carbon impact, this would roughly be equivalent to building another Niagara Falls. The carbon dioxide will be captured from a number of refineries that upgrade oil sands, and that's going to put a significant dent in Canada's tar sands emissions. It's going to reduce the tar sands emissions by about 25% in Canada. Unfortunately, the carbon dioxide from all 4 of those projects I just showed you is used or will be used for enhanced oil recovery. That means that they pump the carbon dioxide into depleted oil fields to pressurize them, and that allows them to extract more oil. That's what makes those 4 projects commercially viable without a carbon tax. But it also makes oil cheaper, and no one's developing a carbon capture storage system for cars, which is mostly where we use the oil. But CCS doesn't have to be done this way. In Norway, they've been pumping 1 megaton per year into the Utsira saline aquifer since 1996. There, the carbon dioxide dissolves in water just like in a soft drink, and that makes the underground water more acidic, so there is a concern that the acid could dissolve the rock capping the formation and allow the carbon dioxide to migrate back to the surface. But they've been monitoring the storage in this field with seismometry and gravitometry, and so far it seems stable. Right now, this looks like the right way to do CCS. This is the largest and longest-lasting saline aquifer project in the world, and they've been able to do that in Norway because they've had a carbon tax since 1991. It's now up to $80 Canadian per ton, and they have to buy cap-and-trade permits on top of that, so it can cost up to $140 per ton to release carbon dioxide in Norway. But they don't have to pay that if they pump the carbon dioxide back underground. So this is a perfect example of how a carbon tax can promote CCS, and the good kind of CCS too. In Canada, we don't have a carbon tax yet, but our government, well, we do in Norway, but we don't have a national carbon tax. But our government has given, we do have a carbon tax in British Columbia, but we don't have a federal one. Our government has given important subsidies, however, to the Quest project, and when that's completed next year, it's expected to beat Norway's record and become the largest saline aquifer CCS project in the world. We're going to have 4 world records in CCS technology right here in Canada, thanks in large measure to the Conservative Party's support for this technology. If saline aquifers don't work, if the acid does turn out to be a problem, or if there's some other problem, then engineers still have a couple more tricks up their sleeves. The carbon dioxide that's being captured and stored in Norway actually comes from underground to begin with. Over there, their natural gas deposits already have carbon dioxide mixed into them, and it's millions of years old. We know that from isotopic analysis. So what that tells us is that the carbon dioxide can stay down there for that long. If we could pump carbon dioxide back into a depleted natural gas well, it would probably stay there for a long time. And there's a big project that's testing exactly that in Algeria right now. If that doesn't work either, we've got more tricks. If we can't store carbon dioxide in a gas state in any way, then what we can do is fix it in biomass. That's what they're doing at the St. Mary's cement kiln, where they capture carbon dioxide from a cement kiln and use it to fertilize algae. So the carbon dioxide gets incorporated into the algae biomass. Now, on this project, they use the algae to make biofuels. They don't store it underground. But you could, instead of making biofuels with it, you could pump the algae into an abandoned coal mine, for example, and then you would actually have carbon capture and storage. The algae needs energy in order to grow, and in this case, they're supplying that with LEDs that are powered by surplus powers from nuclear reactors that are relatively nearby. But you could just use sunlight as your energy source. This is another bioreactor growing algae in Germany. Using algae for carbon capture is a very cutting-edge idea. Right now, they're just using it for biofuels because you can make money from that. In the absence of a carbon tax. But if there was a financial incentive to put carbon back in the ground, then it might make sense to grow algae just for the sake of pumping the sludge deep underground. Over time, that algae would gradually turn back into coal, and we would have succeeded in returning carbon back, or coal, back to its original state. We can accelerate that process of coal formation with a process called pyrolysis to make biochar. James Hansen is a famous supporter of this idea. You do need an energy source for pyrolysis, so that has to come from a clean energy source. But the advantage of biochar over algae is that it is completely stable. Algae might decompose and produce methane if oxygen can get down into the mine shaft. But with biochar, you can just bury it at shallow depths like in a landfill. But biochar isn't garbage. It's actually great stuff for soil. Biochar can fertilize acidic soils and purify water. It can help solve our food, water, and carbon problems all at once. Now you know what carbon capture and storage. And I paused and asked for some questions about this, and there were some great ones which I wish we had caught on tape. But if you have questions about this, feel free to add them to this YouTube video or email me at ytrottier, ytrottier @alum.mit.edu, and I'll try to answer as many questions as I can. But we're not done with the presentation here. We've talked about what carbon capture and storage is, but why do we really need it? Why take the coal out of the ground and then burn it and then get energy to put it back in the coal and put it back underground? Why not just keep the coal in the ground to begin with and plant trees on top? So now I'm about to show you the real magic that why CCS is really useful. And I hope that I'm going to blow your mind with this next trick. The people were really appreciative of this. This amazed some people in Ottawa. If we combine biofuels with carbon capture and storage, we could theoretically start removing carbon dioxide from our atmosphere and go back down to 455 ppm. This is where it gets useful. Let me explain that. This is how traditional fossil fuel combustion works, essentially. We take fossil fuels out of the ground, burn them, and release the carbon dioxide to the atmosphere. This is called carbon positive. And this is the problem that we need to solve. Carbon capture and storage takes those emissions and puts them back underground, where the fossil fuels came from. This is carbon neutral. It stops aggravating the problem, and we might need some extra steps to turn the carbon dioxide into algae of biochar, but it's still basically carbon neutral carbon capture and storage. Now let's look at biofuels. With biofuels, you have plants that take carbon dioxide out of the atmosphere and you burn them to produce energy. The carbon dioxide goes back to the atmosphere, but that's where it came from in the first place. So this is organic carbon, not fossil carbon, and the whole process is carbon neutral, just like carbon capture and storage. Now let's combine them. Grow plants to absorb carbon dioxide out of the atmosphere, burn them to get energy, and then put the carbon dioxide back underground. This system is now carbon negative. Only 3 small plants are doing this so far, but they talk about a lot in the IPCC reports. This is probably necessary in order to have a reasonable assurance of staying below 2 degrees Celsius in this century. And it is absolutely necessary to get our atmosphere back down to 455 ppm carbon dioxide equivalent. But before we can build this, which is the ultimate goal, we're going to have to develop the technologies piecemeal. Develop biofuels and carbon capture and storage separately, and then merge them together. We do already have a sort of low-tech way of doing bioenergy carbon capture and storage. It's called planting trees. And this does help, but it has some sharp limits. You need a tremendous amount of land to have a significant impact, and forests already compete with agriculture for land use. The IPCC has done the numbers, and there just isn't enough land and there just isn't enough land on the planet to rely on this, especially when you think about feeding our future population of 12 billion people in the middle of a mega drought. And that's why the IPCC finds that we must have CCS in order to remove carbon from our atmosphere. This project on this slide comes closest to achieving that dream. The Illinois Basin Decatur project takes 1/10 of a megaton carbon dioxide per year from an ethanol plant, so that's biofuels, and sinks it into a saline aquifer, the right place to put it. This is tiny, but it's a start. Just like renewable energy, wind and solar used to be tiny and was attacked a lot for it at the beginning. The only thing that's wrong with this project is that the biofuels that they're using is corn, so first generation biofuel, and that competes with food production. We need to grow our biofuels on unproductive land and without using freshwater resources, which is going to be another scarce resource because of climate change. So that's probably going to mean algae. Algae is currently grown to make food additives and pharmaceuticals, and that gives us a stepping stone to biofuel production. Algae doesn't have any roots, though. It doesn't actually put any carbon underground. It just grows on its own. So you have to keep harvesting it and pumping it underground in order to have a carbon capture and storage system. And then if we're doing that, we might as well burn it to get the energy before we store the carbon dioxide. Biofuels from waste production will also help, like this one that will use manure from the Toronto Zoo and waste food from a large food distributor to generate biogas. This one is a phenomenal project that you can make money from if you're in the Toronto area while doing good for climate change, because they're currently looking for investments to get this built. I invite you to look up ZooShare on the internet to find out more about this if you live in the Toronto area and you have some money to invest. Well, I always, when preparing these talks, I always imagine myself facing some very difficult audiences. Okay, so what does this have to do with carbon fee and dividend? And what does this have to do with Citizens Climate Lobby, which was the group for which I prepared this presentation? Well, take a look at this quote from the IPCC. CCS power plants will only be deployed if they are either required by regulation or the cost differential between them and the unabated counterpart is overcome. For example, by sufficiently high carbon prices. And again, that's not opinion, that's science. CCL supports putting a fee on carbon at the wellhead. And if you do that, then the Boundary Dam project will pay the same fee as a coal plant that just releases its carbon into the atmosphere. Why would anyone want to go to the expense of building a CCS plant if it doesn't save them any money? What I propose, and I hope we can have some discussion about this, is that our proposal, our fee and dividend proposal, should be modified to give a carbon credit to companies that sink carbon into the ground. Here's how that would work. The coal mine pays a carbon fee when they take it out of the ground. They now have to sell coal at a higher price to pass on their costs to their customers, the power plants. Then we promise to increase the carbon fee until the coal plants just aren't profitable anymore. The coal plants are going to see this coming, so they're going to cap their smokestacks, just as Boundary Dam did. Then they receive credits for the carbon dioxide that they pump underground, and that offsets the higher costs that they're paying for coal, and that means they can stay in business. But here's the best part. Everybody gets to keep their job. Nobody has to be retrained, and no expensive equipment has to be replaced. Boundary Dam was built in 1970, but they were able to refit it with carbon capture and storage this year in 2014. So that proves, in my mind, that we can refit old coal plants. Now, there are some more complicated situations that we need to look at in order to draft a good economic policy. Let's look again at the Weyburn-Midale project. The Great Plains Synfuel plant that produces the carbon dioxide is on the other side of the border from us. So where do you apply a carbon fee? Where do you apply a fee on the carbon? Ideally, you want to apply the fee on the coal as it comes out of the ground. But now suppose that Canada gets fee and dividend before the United States does. Then we would want to apply a border tax adjustment on the carbon dioxide as it flows through a pipeline into our country. But wait a second. Border tax adjustments are supposed to be symmetric. So if we were exporting carbon dioxide, would that get a credit? It's something to think about in working out the details of the policy. Then the carbon dioxide gets pumped underground, and I'm arguing that Weyburn should get a credit for that would cancel out the border tax adjustment that they paid at the border. Why is that? Because otherwise, the synfuel plant is just going to go back to dumping carbon dioxide into our atmosphere. Because that would be cheaper than sending it over the border and paying the border adjustment. But now over here, after the carbon dioxide is sent underground and we pull fresh oil out of the ground, I think everybody can agree that we should apply a fee at the oil wellhead here. Some people don't like my idea of giving credits for stored carbon because they'd like to get rid of the fossil fuel industry altogether, regardless of whether or not it pollutes. But I think that the strongest argument for giving credits to stored carbon is this. The ultimate goal is to get to bioenergy carbon capture and storage, that merger of biofuels and CCS. And this is never going to work financially unless these plants somehow receive money in recognition of having removed carbon from the atmosphere and put it back underground where it belongs. I was very happy in talking to some people after the show that they said that some hardcore environmentalists who said that I had really changed their mind on CCS and made them more open to the idea. And that's really important because according to the IPCC itself, one of the biggest challenges that carbon capture and storage faces is public acceptance. There is a good reason to be skeptical of the fossil fuel industry at this point, and there is a fear that could turn into opposition, sometimes irrational opposition to carbon capture and storage. So I hope that at least today you've learned a bit more facts and you'll be able to make a more informed decision. Again, if you have any questions, I invite you to write to me or to add your questions under this YouTube video. Thank you very much for listening.